Alrighty, let's talk about what happens to a charged particle when it tries to move through a magnetic field. In the interest of time, I'm not going to write the notes along with you. I'm going to try and make this as short as possible. So I'm actually just using my notes from last year. Okay, so just a reminder, field forces, essentially the pattern we found in the past is that you have a field force. That field will exert a force only on certain particles that have like the correct properties. For example, gravitational field. It only acts on particles that have mass. Mass is like the thing that creates the gravitational field, and then the gravitational field exerts the force on a mass. And that force is the mass of the particle times the gravitational field. Or when we did electric field. Electric field is caused by charged particles, and it only exerts force on charged particles, and the force it exerts is the charge of the particle times the electric field. So magnetic field is similar, but also breaks the pattern a little bit. So if we followed the pattern, there should be a magnetic field caused by something that is magnetic, and then the field should exert a force on things that are magnetic, and it does, okay? Magnetic fields do act on ferromagnetic objects, magnets, and they do, but we in this class don't really care about that. Just when we were talking about magnets the other day, I said that like magnets are awesome. I love magnets. Everybody loves magnets. They're so cool. Okay, but we don't really care about them in this class. We just care that they create a magnetic field, and then we talk about what the magnetic field does to things. And or later, we're going to talk about how certain things can create magnetic fields, certain things that are not magnets. Anyway, so magnetic field does exert a force on magnets, but it will also exert a force on another kind of particle, a particle with these properties. Okay, so I'm going to go over all three of these. Let me, can I make this bigger? Well, no, I'll just leave it. Okay, so number one, the particle has to have a non-zero net charge. So it's a charged particle, okay? Number two, that charged particle must be moving relative to the magnetic field, okay? That's a little weird, but that's true, okay? A charged particle just sitting there at rest relative to the magnetic field will not feel a force from the magnetic field, okay? But a charged particle that is moving, and number three, it is moving in a direction that is not parallel to the magnetic field. If you have all three of these things true about this particle, that particle is going to feel a force from the magnetic field. That is, the magnetic field is going to exert a force on this particle. All three have to be. It's got to be all three. So if you had a charged particle that was moving, but it was moving parallel to the magnetic field, no force. If you had a particle that was moving, say perpendicular to the magnetic field, but it wasn't charged, no force. Okay. If you have a charged particle that's just sitting there, no force. Okay. Now, when you've got all three of these things, the force that the magnetic field exerts on that charged particle is this much. Okay. The force is equal to the charge of the charged particle multiplied by its velocity. Okay, so that's going to be a vector because velocity is a vector. And then you have to cross product it with the vector for the magnetic field. Okay, so it is a cross product. That's why we had to have the velocity being non-parallel to magnetic field, because if velocity was parallel, the cross product would have been 0. Okay. If you want to look at that instead of as a cross product, but instead as finding magnitudes of the force using the magnitudes of the vectors, this is a standard, what you get when you get a cross product. The magnitude of the answer of the cross product is this. So the magnitude of the force exerted on that particle in newtons is going to be charge times speed times magnitude of magnetic field times the sine of the angle between the direction of velocity vector and magnetic field vector. Okay, please note that when you're using this equation, you need everything to be in standard units. So that force had better be in newtons, that charge better be in coulombs, speed's got to be meters per second, and magnetic field needs to be in Teslas. Okay. Okay. So if you want to use that for magnitude to find the direction of the force, you're going to use a right hand rule. Okay. So again, you can just do a cross product, and you could do it like in vector notation, and the force will come out as a vector in vector notation. It'll tell you exactly which direction the force is in. But if you're using this blue one and you're just finding the magnitude, then in addition to that, you have to find the direction separately using a right hand rule. So this is my attempt at a drawing of a right hand. Woof. Okay. Okay. So you stick out your right hand. Okay. Point your fingers along the direction of the magnetic field and point your thumb along the direction of the velocity vector. Okay. If you do that, the force exerted on a positive charge is the way your palm points. So if we were in class, I literally think of it as you literally push it with your hand. Okay. It's like you're pushing that, say it's a proton, with your hand. That is the way it literally is pushed. It experiences a force in that direction. Okay. A negative object, however, is opposite. Okay. So stick your fingers in the direction of magnetic field, stick your thumb in the direction of velocity, and if it's an electron, it's going to get essentially backhanded. Okay. The force is in the direction of like as if you were pushing it with the back of your hand. Okay. So positive charges get like slapped, and negative charges get backhanded. It's kind of violent, sorry, but I don't know, it's funny when you do it in class anyways. Here's some examples. Unfortunately, the answers are already on here. When we do this in class, like the blue answer will not be in there. You can see like this first one in the upper left, that is a magnetic field is coming out of the page at you. That's how you draw vectors that are coming out of the page at you, if you don't remember, the dots. So if I stick my fingers, they're pointing like literally at me, and then I need my thumb up. That's a positive object, so my palm is facing to the right, and a positive object would get pushed to the right. This one we have, stick your fingers up and to the right, velocity is to the right, and the palm ends up facing me, and that's a positive charge, so the force is facing me. Okay, here we go. Fingers up, thumb to the right. Okay, but it's a negative object. My right hand, the back of my right hand is facing away from me, so the force is away from me. So you've got this X for showing the vector going into the page. And then finally we have here magnetic field and velocity they are parallel or anti-parallel. The cross product will be 0. There's no force here. Okay. Oftentimes you will be asked to talk about the special case of when not only is velocity not parallel to magnetic field, but it is literally perpendicular. This is a nice one because if your V and B are perpendicular to each other, then you're doing the sine of 90, which is 1. So the force just becomes QVB. That's it. And then the force is perpendicular to both V and B. So here's a little picture of a situation where that might happen. I've got magnetic field coming out of the page. And this picture, velocity was down at this moment. So if you do your right hand rule, it's a positive charge under there. The force was to the left. Here's the thing. What will end up happening is because the force is perpendicular to velocity, it's a centripetal force is what it is. Okay. Think of the velocity as that's tangential velocity. If there's a force perpendicular to that pointing, that's going to be toward the center of a circle. And what ends up happening is, as long as everything's constant, so as long as like the magnetic field is constant and you don't actually leave it, this thing's going to move in a circle with a speed of v and some radius r. And a very common problem that you will see I've seen it on an FRQ. I've also seen it on multiple choice problems. Is they will give you enough information and then they'll ask you things like, what's the radius of the circle that this thing makes? Or they'll tell you the radius and they'll ask for like the magnetic field magnitude, or I don't know, there's a lot of them, okay? They love these. But the way you figure all of those out is you always start with, like everything, Newton's second law, F net equals ma. But in this case, this thing's going to move in a circle, so that a becomes centripetal acceleration, which is v squared over r. If you set that up, and then the force is the force due to the magnetic field, which is this much, qvb. So if you set that up, these cancel and you end up with like this, and you proceed from here for whatever it is you wanted to solve for, whatever the problem is. Okay. If you look in our notes on our class notebook, there are some practice problems that we did in class about where we do this. I'm not going to include them on this video because it's past 10 minutes now and that's enough. But you should go look at the notes page that we did in class while you guys were off on your senior skip day. I hope you have fun.